Okay, so you guys should be good with submitting Project 1 Phase 2. The submission opens today. You can refresh your submit server and the upload option should be made available to you. Today, let us complete path planning by discussing two important algorithms. Till now we have discussed Dijkstra and A Star, and they are graph-based algorithms, but there is one part that we haven't discussed, which we mentioned, which is the probabilistic part, which is the sampling-based algorithm. One of the things that we will be discussing today are PRTs, which are probabilistic roadmaps, and we will also discuss RRT. Once we are done with that, we will be talking a bit about D Star, which is a fancy A Star, which is a dynamic graph-based planning algorithm. We already discussed why A Star is better than a naive algorithm like Dijkstra, but D Star takes it one step further. We will come to that as we proceed. So let us first discuss roadmaps. I hope all of you remember C free, C occupied, C obstacle, whatever. So the first thing that we talk about is roadmaps, right? What are roadmaps? This nice figure that you see here, full of dots, is basically constructed by taking your obstacle. Let's see this better. Let's say that this is my C world, which is everything, and I'm just taking a simple example of two obstacles, right? These are my two obstacles. What we now do is we partition this space, right, into spaces where there are obstacles and spaces where there are no obstacles, right? So let's say, so the way this creation of these roadmaps goes is that you drop a line from one top edge to one of the vertices of your obstacle. You can go from left to right. So let's drop that. We stop here. And then again, from here, we drop another line to the bottom, right? What happens then is that I pick a point. So what you can see here is that this part, this area right here, this rectangle, we take the middle of that rectangle and we choose that to be one of the nodes. For each of these two lines, now you have to treat them as two different lines, because this is one line till this point and this is another line till this point. We take the middle of those two. This is not the middle, but forgive me. So now we continue this way. So right now what you can see is we have three nodes already, and we continue to drop. We pick the center and we pick the center. Now obviously this is a trapezoid, right? Which means that you know how to compute the center of a trapezoid, and we pick that to be one of the nodes per trapezoid. The same goes here. We drop, select, middle, so on and so forth, until we have covered the entirety of our C world. We can now proceed to use these nodes as a way of planning our roadmap, which means that if we take the leftmost node to be our start point, we can start to connect these nodes in such a way that we get a valid path, right? Which means that if you look, there is no line that goes through an obstacle. The way we have constructed our roadmap ensures that we have only the nodes available in our free space, right? And then once we have connected all of these nodes, we again go from left to right. Once we have connected all of these nodes, what we end up getting is a connected graph, and we can follow that using whatever shortest path or whatever we choose to get from our start to our goal. So that is the basic concept of how to create and use a roadmap to plan your path from start to goal. Okay. That was a quick introduction. Let's get to the meat of today's lecture, which is RRTs, which is rapidly exploring random trees, right? The algorithm was given by Kuffner and Lavalle, and I'm sure you guys have read the Lavalle textbook on planning. It's the same guy. You should, if you haven't read, you should go through the Lavalle textbook because it is super comprehensive and it is the recommended text for planning. Normal RRTs, like the basic ones, come in three flavors, right? One of them is a single tree, one of them is a bidirectional tree, and you can have a forest of multiple trees together, right? So you can also augment RRTs with differential constraints, right? Which means that if you just were to plot a path, that's not useful, right? As we explained that in your course, you will be first doing the path planning for, let's say, a drone, and you will then be converting that into a trajectory, right? Which is something that the drone can actually follow. Now, you can incorporate those constraints into RRT to give you directly a valid trajectory, which means that, let's say you have a car, right? You want the car to go from point A to point B. RRT will give you the path, right? But the car might not be able to take a turn at a certain juncture, right? So if you have a point here and then RRT tells you to go here, your car has to follow a certain angle, right? Based on its wheels, based on how big the car is, etc., etc. So those are what we call kinodynamic constraints, right? So you can incorporate that as part of your RRT planning process. You also have non-holonomic robots, right? Non-holonomic robots, how many of you are familiar with non-holonomic robots? One of you just, yeah.
Yeah, so a robot with constraints on its degree of freedom, so it can move only in a certain way.
Correct. Which means that a car is an example of a non-holonomic robot, which means that ideally it's an object in 2D space, right? It can't fly, not yet anyway. But the idea is that the car can, even though it is supposed to move freely in X and Y space, you still have certain constraints based on the wheel, right? So that becomes a constraint and it is under actuated, as we say, which means that that's an example of a non-holonomic robot. So again, you should be able to incorporate non-holonomic robots into your RRT to give you an actual applicable planning. So any questions till here? We will be discussing single tree and bidirectional trees later on, but any questions in roadmaps or what was explained till now?
We don't have any non-holonomic versions of the drone.
Yeah, drones are again.
They have all 6 degrees of freedom.
Not really, because if you think about it, a drone does not exactly translate, right? You have a certain kinematics of the drone, the dynamics of the drone. So it's not, a drone is actually, that's a good question. A drone is actually a non-holonomic robot. It does not exactly translate left and right. There is a certain dynamics to it, which means that it has to tilt before it can translate in one of these ways.
No, but then for a car, for example, if you're planning for a car, you can't have 90-degree turns, right?
That's correct.
For a drone, you can.
Yeah, but then the car's degrees of freedom and the drone's degrees of freedom are different, which means that their definition of holonomicity will be different.
Yeah, but then from a planning point of view?
From a planning point of view, that's why you have the trajectory planner, right? Only the path is not enough.
Correct.
You also need to convert it into something which, so that comes under kinodynamic constraints, not exactly under the holonomic constraints. So just to keep that clear. Just the path again will not be sufficient, because your path must not have, let's say, a sharp banking, right? In a car, for example, roads are designed in such a way that when you're taking a turn, they are banked, right? That's undergrad high school physics, like why are roads banked? But you need to take those things into account when you are doing RRT.
What is an example of a holonomic robot?
Okay.
Every robot will have a constraint.
No, we have a holonomic robot downstairs in the art lab. It's called the Ridgeback. It has holonomic wheels, which means that it can directly translate front, back, left, right in any angle as you wish. So that is an holonomic robot. So you can Google, if you guys want to see what it looks like, you should Google ClearPath Ridgeback. So you will get a good idea. It's a mobile base which can translate in all directions. So it's not under actuated at all.
But it can fly, so it can't go in the Z direction now.
Yeah, but the degrees of freedom of the robot does not include the Z direction anyway. So what is the idea? The idea is that if you have a thing which has a certain specified number of degrees of freedom, can it move in all those degrees of freedom? Which means that this robot has only X and Y movement, and it can move exactly along all those dimensions. So that's what I was saying. Holonomicity depends on the degrees of freedom
You
of the
can
robot.
qualify that by saying this is a holonomic system on the plane.
Yeah. That's
So you
correct.
make sure this is not included, okay?
Yeah.
And you can say that the drone is a non-holonomic system in 3D space.
So, okay. So that's the basic intro to RRTs. We will get into how it works. So, So look at that figure, right? You have a set of points. One of them is the initial point. You have a new point, which is in green, and you have a nearby point, nearest point to that new point. And so the algorithm is like super simple, right? You pick a random point in your given space, right? Then what you do is you try and connect it to the rest of your tree, which means that you already have, let's say that you already have a few points. So you try and connect that new point to the rest of your tree. But as we mentioned in the previous slide, you cannot just plug it in. You have to maintain all your constraints. You have to maintain obstacle avoidance. You have to maintain collision avoidance. So what you do is you pick a point and then you try and connect it to the rest of your tree. But if there are obstacles, obviously you can't add that, right? If there are certain violation of your constraints, which means that again, if let's say the robot cannot be there because it's too narrow or because there is a sharp turn or something, then again you fail. If all of your constraints and all of your obstacles, etc., avoidance is satisfied, you attach it back to the tree. Otherwise, pick a new point and keep doing this iteratively until you have your tree from start to your end, right? Super simple. We must discuss a bit about Voronoi diagrams, right? Because you will see why this is important as we proceed into RRT. Let's say you pick a point, right? You have a space and you pick a point. You have a set of such points in your space, right? So a Voronoi diagram takes each point x of I in your set of points x and it decomposes the space around that point into some region R, right? You can have a point and this region around it is called the Voronoi region, right? This point is selected in such a way that it satisfies a very special property, right? What is that property? Any point P, any new point P in this region is closer to x of I than any other point, which means that if you had another Voronoi region, actually this is wrong, it should be proper lines, but yeah. Any point P in this region will be closer to x of I than any other points, x of k, let's say. And what that allows you to do is get a figure like that. That has been taken from a sample MATLAB code, right? You can literally do this. You can have an array of x points, you can have an array of y points, and you can just call the Voronoi function on that set of points. It will do this computation for you. It will divide up your grid, your world, into these kind of little regions, right? Why is this important, right? This process is what we call partitioning of spaces, right? The actual math behind constructing this you can check out, but just keep in mind this diagram, right? Any?
So how do you define the region of influence here?
You do it using half spaces. The way this is actually constructed is using half spaces, right? Given a point, you draw a half space which keeps the point on one side and the other, and then you take the next point and then you draw its half space, and basically you start doing intersections of half spaces. And then as you proceed through each of your points on x of I, you adjust the previous half spaces by taking their intersection such that you reach this figure.
Yeah. So take those 2 points, connect them, and bring the perpendicular at the middle. Take those 2 points, connect them, and bring the perpendicular at the middle. Take those 2 points, connect them, and bring the perpendicular at the middle. Take those 2 points, connect them, and bring the perpendicular. And that's the algorithm. You know, this idea of the Voronoi diagram is much deeper. It's also used, most probably, to represent categories. So you can imagine that this is some kind of taste space. Taste. So here you have sweet, and here you have sour. I mean, there's a few basic tastes, right? So we can increase the dimensions. Let's keep it 2 so that we see it, because you can have Voronoi diagrams in any dimension. In 3 dimensions, in 4 dimensions, in 5 dimensions, in n dimensions. Yeah? So, for this combination of sweet and sour, you have this taste of this particular food characteristic. Yeah? And then you have this other taste, and this other taste. And now you want to characterize that space. You get a measurement. You have to find to which one is closest. So there are many calculations in artificial intelligence where when you make a measurement, and then you have to find out that measurement is closest to what that you already know. Yeah? Voronoi diagram is the natural way of doing it. You take the space that you have, you create the Voronoi diagram, and now you have a natural way of saying, well, all these guys are closest to this, because I have unclosed them with a polygon. So if they fall inside there, if they fall inside here, I know that they are closest to this. And they get a label. Similarly here, you can consider them for planning of the path.
So, as the professor was mentioning, one of the useful ways of using Voronoi diagrams is for k-means clustering, right? You can, because you know your set of seed points, given a new point, you can quickly figure out which region it belongs to, right? Another very interesting property that you should know about is that the size of the region decides the influence of that point on a new point, which means that the larger the size, obviously the larger its region of influence. So these are two things that you should, yeah.
So are Voronoi diagram representations more computationally efficient than just directly checking which points you're closer to by like if you have a new point, you could just take distances to all the points in your database directly and find the closest, or you could use the half space Voronoi representation as one more.
Yeah, I mean, this is more efficient because this is a priori, right? You compute this once, and basically what you have is a set of regions, right? And then you can, given these lines, you can quickly find out if something lies in the region or out of the region.
Yeah, but then you have to do that for every region, right? Until
Yeah,
you find
so
the right region.
that is usually faster than doing k-means for the whole set of points, like computationally. And I mean, the real reason for this we'll see how it.
I'm sorry, if you have a point and another set of points, in order to find out, you have to consider the distance of the point from all the points. Here you don't. You know you are in that region.
Well, then
That's
you
the
have to
difference.
figure out that you're in the region by comparing to all the half spaces in your representation.
Well, no, you can, this is immediate, like, you know, if you are on the plane, for example, I give you a point, and I have the definitions of the lines, I can in constant time find out where you are.
I mean, one thing you can think of is that each of these spaces are convex polygons. And to find if a point lies in a polygon is super fast, constant time.
Yeah.
That's why this is better than doing point-to-point k-means. Because, as I said, this property becomes super important, right? Given any new point, if you place it in one of these regions, that point will be closest to the seed point than any other point, which means that automatically you have your information just by putting it in one of these polygons.
Okay. How does this compare to having Gaussians at every one of those points?
Yeah, that is another type of planning, which is the field, right? So that's a little slower because you can get stuck in a local minimum. That's not always a good thing. Okay, so just a little segue. What he's talking about is another kind of planning, which I didn't mention, but
It was very mathematical and people liked it, but it hasn't found too many.
exactly. But it's very interesting because it's based
Imagine
on.
you are in some space that has obstacles and you grow a vector field.
Yes.
And the vectors are telling you whether you can move.
Yeah.
So those vector fields will be like, you know, if you
Gaussians.
have an obstacle and water is running, right? So, anyway.
Okay, so yeah, just to visualize what the professor is saying, let's say that this is an obstacle, right? We treat them as point obstacles, and we say that depending on the size of my obstacle, I draw a negatively charged field around it. And you can treat that as a Gaussian with the obstacle at the center, right? So as you get closer, the effects of that negative field increases, and as you move away, it goes away, right? So if we treat it that way, and let's say that this is my start point, and this is my end or my goal, right? I have the robot, and we treat it again similarly, but this time with a negative charge. This also has a negative charge because, as you know, negative repels. Same like a magnetic pole or whatever. This, again, same thing based on its size. We treat the Gaussian and we widen it or make it thinner, higher or taller depending on what the influence we want, right? We then give the goal a really high positive charge because that's where we want to go. We want this guy to get attracted to this guy. Now we are moving, right? We are moving. We come here, right? At this point, you have a repulsion. And depending on how close you are, the repulsion is stronger or lesser. And the obvious reaction that happens is because these are forces, you get a negative repulsion force, which means that in the next step you shoot away. All the while being attracted to your goal.
So basically what Kaniska is saying is that there is a kind of planning that you can think of as an electromagnetic analog. So you are here, you want to go there. Call yourself negative, call that positive, so that it can attract you. Now put obstacles. Obstacles, call them negative. You cannot. Now you have to move. Your negatively charged thing, it has to move. It is attracted by the goal, but it has to avoid all the other negative charges. Now, if you write down the math for this, it becomes very interesting because you have a system of forces. And
Inverse square.
what happens is, ultimately, you can create a field. A field. And this field will be all the possible paths. Because when this guy will go here, okay, so you may go like that. So basically you will have, fields like this. There will be, if these are obstacles, the fields, will be very dense around the obstacles. If the goal is here, that's how it will be. If the goal is there and you're here, then it will be different. So, if you have a good understanding about electricity and magnetism, what I'm saying should be trivial to you. Okay? So in other words, you set a problem like that, and then you do the math for that particular space you have, and now you have a field. And now you can go to the goal by following the field line, some field lines. That's it. That's the technique. Very beautiful, because it has this science analog, but it hasn't really found many applications yet. It's not the preferred technique.
I mean, yeah, so one of the reasons for that is because depending on the force of this might never get attracted, right? So what you can have is, let's say there are two obstacles, right? Each with somewhat intersecting flow fields. What will happen is, it will go there, it will get repelled, it will try to move towards it, it will get repelled, and it gets stuck in a local minima. It gets stuck in a local minima.
Right.
So, unless you have,
You can understand how that could happen. If you play with the charges and so on, you're supposed to go like that, and then you end up going, totally different way.
Because this is your global optimum, right? Your goal, which is the idea. But if there are two obstacles, it comes closer, there is a repulsive force, it tries to shoot back, again it comes, shoots back, and you have that oscillatory effect, which means that you will never be able to get to the goal unless there is some way to nudge it out of that deadlock. And that becomes an issue. RRT tries to solve that though, right? We will see how. Remember this, and we will proceed. We come to the concept of using RRTs for Voronoi biasing, right? That's a small little animation, thanks to Wikipedia, which tells you how RRT proceeds, right? Take a moment to observe. You can see how it starts relatively sparse, okay, in the beginning, moving towards the four corners immediately, pretty much. And then suddenly it becomes super dense, right? That's where the rapidly exploring term comes from, because it immediately blows up and covers your entire space, right? Where that is related to Voronoi biasing, let's discuss. The idea is that given a uniform sampling, right, of your space, because this is a sampling based algorithm, which means that we don't want to select points from one region only. We want a uniform sampling of our space. Given that, the probability of proceeding from an existing state to a new unknown state is proportional to the size of the Voronoi region of that point, which means that if I had my tree till, let's say, here and something, right? I want to connect a new point here, right? The probability that this point will attach to this and not any of the others is directly proportional to the Voronoi region of that point, right? That's where we realize that the size of the Voronoi region is the so-called area of influence becomes important, right? Since the largest Voronoi region, right, which means that if you just have a set of points and you are beginning your search, right, you start from some init point, what is the Voronoi region for this point? Let's say this is your Q init, right? What is the Voronoi region for this point? Everything, right? We pick another point, let's say something like this. We do that division. What happens is, and this is completely incorrect, but just to give you the idea, in this case, the largest Voronoi region is the last point, everything in front of that last point. So, given that property that the expanding of an existing state, which means that this is an existing state, the expansion of this existing state depends on the Voronoi region, and the fact that the largest Voronoi region belongs to the point that was most recent, right? If you combine these two, what happens is that there is an inbuilt preference in RRT to start expanding into newer regions, which means that I start here, I go here, again, let's say I break that up into two, so on and so forth. We keep breaking bigger and bigger Voronoi regions into smaller and smaller regions. That is the essence of RRTs, right? That link, once the slide is up, take a look. That is from Lavalle, and he explains very well why this Voronoi biasing happens. It's not something that is programmed into it, right? We discussed the algorithm. There was nothing regarding this. It just so happens. So, as I was saying, why is this good? Because in case of things like, let's say, we don't do RRT, right? We take a simple, naive, random point. Okay, let's say this is my point. Let's say we do a naive exploration, right? We take a random point, we put it, try to go. If you don't have this biasing, right, what will happen is all your points will be super clustered around the search region. You have no incentive to move into unexplored areas. That is one important thing that RRT solves. As I was saying, all the new points are clustered around the start vertex because you have no motivation to move away from that explored area, right? But the whole point of planning is that you want to manage greedy versus exploration. Same thing with random walk. Random walk is another popular algorithm. Who knows about random walks? Can anyone explain random walks? Okay, I will explain random walks. Random walk basically is the simplest explanation of that concept is that, let's say I have a number line, okay? I separate that into 0, -5, let's say, and +5, right? I am at 0. I flip a coin. I get a head. If I get a head, I move +1. If I get a tail, I move -1, right? So random walk basically is the algorithm which selects a certain path given a certain probability, right? So that's what random walk is. Now if you apply this concept, let's say, to your planning, again the same problem, right? You flip a coin, you move, let's say, x +1 and y -2, let's say, and if it's a tail, then you move x -2 and y+. But that still does not solve the problem of moving away from your initial position. Sure, you will get there in the end, but that's not what we want. We have a time limit constraint. We want to get there now or as soon as possible. Random walk also suffers the same issue. But because RRT depends on the nearest neighbors, right, as we discussed, which is that the next point will be connected to the nearest point, right? What that means is that the largest Voronoi region areas are selected at every iteration. And as a result, the bigger points start getting broken up into smaller and smaller points. Those three pictures can describe that very nicely. In the first one, let's say that you have done a few number of iterations. You can already see that the path is sparse, but it has extended towards the corners immediately. I think that's 50 iterations, I'm not sure, but it's a very small number of iterations. As you move further, you can see that it starts to encroach deeper and deeper into unexplored corners, and finally you can see that pretty much all of your free space or your world has been covered. So it is efficient. So this is sorry.
Do you realize what's happening with a random walk? If the random walk is unbiased, that means the probability of moving to the right or moving to the left is the same. Yeah. So if you let a system with such a random walk go on, what do you expect to happen?
Stay original.
You will be around, you will be going back and forth. So in order for interesting things to happen, you have to bias. So these are like Markov chains. Markov chains. Okay, sorry for taking time for this, but since it came up, let's give a very simple example. Let's say you have this possible 4 states. You can have n. Okay, and you have a particle that is going to move to the right with some probability p, and it's going to move to the left with some probability 1 minus p. So you can play with the p. Yeah? So now you can build a probability matrix, a transition matrix. 1, 2, 3, 4, 1, 2, 3, 4. So from state, okay, when you have such situations, you can have absorbing boundaries or you can have reflecting boundaries. In other words, if you come here, you are absorbed, you stay here forever. That's absorbing boundaries. Or if you come here again, or you have reflecting boundaries. If you come here, you are bounced back. Okay? So let us say you have reflecting boundaries. So if you are at 1, right? What is your next state? You will go to 2. If you are at 1, you will go to 2, right? With probability 1. The rest will be 0 because these are stochastic matrices. And stochastic matrices have columns that add up to 0, to 1. Okay? So 2. From 2, you can go to 1 with probability 1 minus p. And you can go to 3 with probability p. And the others are 0. You get the point? So now you make a matrix here. I'm not going to complete it. So this is your transition matrix. So now take your initial state, x0, which is the probabilities on where the particle is. Let's say the particle is at state 2 to begin with. That means this is the initial state. These are the probabilities of where the particle is. So now you want to see where is the particle going to be in 1 move, in 2 moves, in 3 moves, in n moves. You take that matrix, p, to the power of n times the initial vector. That is going to give you the probabilities of where the particle is after n steps. And it turns out that if this, under some conditions, this converges. If you have a Markov chain and the matrix doesn't change, the probabilities don't change, then this will converge to some equilibrium solution after several steps. The probabilities will not change anymore. When you compute this as n increases, this result will be the same. Okay? So what is happening with those random walks, what Kaniska is saying, this thing, because it operates with the size of the Voronoi region, is biasing the random walk. This is why, you know, like it has this property that it starts here and it's just going. It's going to cover. It's going. It is biased. Okay, and those probabilities are proportional to the size of the Voronoi. Okay, many of these things you can't prove, actually. There are some interesting, very difficult proofs. Whenever you have probability and geometry, it is extremely difficult to prove something. Okay? I mean, if you prove something, you are staying forever. Like the Buffon needle. You know the Buffon needle? If you have a set of lines, parallel lines, on the plane, and you have a needle of some length, and you can give constraints to that length, and you throw it, what's the probability that it will cross one of the lines? Did you understand the question? If you have time in a weekend and you don't know what to do, try to solve this. Okay, it's called the Buffon needle. You can even Google it. So you have now a needle. And you're gonna make also this, to make it more interesting, to be longer than the distance between the lines. And now you throw this, these lines are on the plane, and you throw the needle randomly. And now the needle is gonna, what's the probability that it's going to cross one of the lines?
Project 1, Phase 3. Submissions due
Anyway, I
next
just want
Monday.
to say that if you say, okay, now let me do some math, and let me try to take into account the Voronoi diagram areas, you know, and the probabilities of the random walk, it may be equivalent to the dissertation. That is why this guy, in his book, he sort of reasons why this is the
Yeah.
case.
I mean, just
without
read the
making
Lavalle
an
paper.
explicit proof.
Read the Lavalle paper if you have time. I mean, that's a really interesting paper where he gives a very simple explanation of why this happens. It's like Professor said, that there is no high level math as such, but the intuition behind it is super elegant, and you should definitely read up the RRT. Also, check out Professor Howie Choset's slides. A lot of the text has been taken from his slides. There is a slide on A Star and D Star, which you should definitely check out. Again, very well explained. So you understand now why and how Voronoi biasing works. It's not an explicit bias. It just so happens that because we are taking nearest neighbors and not the whatever, like the nearest point, it makes it biased towards larger Voronoi spaces, right? Since we are on the topic of biases, let's discuss some other biases, right? Yeah.
So the map is a continuous space, right? In the
Exactly.
And you build the Voronoi diagram on the go.
Yeah. You build it. You can also do it a priori, as I was saying. You know, you can pick your random points. You can put everything there and set it up initially.
Then where do you stop? When do you stop?
So now you're getting into the convergence properties of RRT, right? So you are correct in saying that this algorithm is a continuous algorithm, right? Which means that you can go as small as you want. It depends on as you remember when I was discussing the basics of planning, there is always a trade-off, right, between accuracy and performance. Which means that if you want something super accurate, your performance is going to suffer. But if you want something relatively, you don't care too much about the accuracy, you can always improve performance. So when do you stop is a very important criteria, because you can always stop when you reach the goal, but that might not always converge, right? So so just skipping ahead one slide, this is an example of probabilistic complete, right? Which means that your probability of picking the goal or finding a path increases, tends to 1 as your number of iterations tends to infinity, which means you will always have that trade-off about when to stop. But in this case, you're right that the Voronoi diagram is, you don't need to explicitly create the Voronoi diagram. It just so happens that when you are doing RRT, this property is exhibited that every new point which is added to the tree is biased towards larger Voronoi regions. You're not in the algorithm, you're not explicitly creating the Voronoi diagram. Let's just be clear about that. You're not creating the diagram. It just so happens that if you did, you would notice this property. Let's just put it that way.
You use the trapezoidal thing, you extend at the first to find the closest point, right?
That's a different one. That's different. That's what we call probability roadmaps.
So you are not basically building a Voronoi diagram. Now how do you know the closest point to the tree?
Because you know the locations, right? I mean, that's, your map is a continuous space, right? Which means that you are able to very easily pick out locations, right? You can say that if my map goes from, let's say, 0, 0 to 100, 100, right? How do I pick a point? How would I pick a point? That's correct, but it's a continuous space, right? There are no specific coordinates. You can go as deep as you want. Which means that your x value will be some random integer between 0 and 100, and your y value will be some random integer between 0 and 100. But how small you want this randomness to be? Which means that do you want it to be 1.0001 or do you want it to be 1.1 or whatever, right? That is the trade-off that I'm talking about. So your tree can be super dense, right? Based on how many it's not discretization, but how small your random values are. So that's how you pick a point. So you're not exactly creating any this thing, right? You're not creating a Voronoi diagram. You pick a point, you say that this is my next point. I know the xy for this, I know the xy for this, and I can just connect them, right? Connect them, not physically, but in my data structure, I can say that, okay, x1, y1 is connected to x2, y2. That's how I build the tree. So you are not explicitly constructing the Voronoi diagram.
When you get the third point,
Sorry?
you need to decide which one to connect.
Exactly, Euclidean distance.
Okay, so you just compare to each one.
Yeah.
So it's going to get slower and slower when you are getting more.
Ideally, but there are ways of, because see, you are not going to connect it to anything, right? You're only going to, you will obviously set a threshold as well, right? You will obviously set a threshold. So that's one of the things that we'll just discuss, is that we discussed this, that larger spaces is obviously causes more exploration, right? So that's one way to ensure that you're seeing everything. Another common technique to do in RRT is to limit the length of the path, which means that if I have a path that is, let's say, valid, I want to limit the length, which means that I get a more focused search. If my obstacles are too small, for example, I don't want super huge lines. So that's one way you limit the length of the path that is being generated.
Various heuristics, like for example, let's say the space is this one, and all the obstacles are the tables and the chairs and all of that. And I want to go from here, you know, to where the lady in the class is sitting at the end. Okay, so what am I going to do according to this technique? I'm going to start here, right? Suppose I have a Voronoi diagram that is given, because I know that space, okay? So I could play with those points like that, but fundamentally, from here, I'm growing. So I can pick another one. Pick another one. Now, when I'm here, I may go there, I may go here, but I know where I want to go. I may be able to go from here, I may go here and get a dead end and come back, or I go here. You get the point. So now what he's saying is you can save yourself or you can be brave. So how much do you allow yourself to move in every step? Yeah? The smaller you move, the safer you are. But the more work you have to do. So you move here, you move here, you move here. Or you can get a bigger thing. Okay? You move here, boom, that's my first. Move here, boom, my second. Bad choice. There's always an optimal. Very hard to find what this optimal is. So most working solutions have heuristics. Okay? So if I had to have a heuristic for this room, I would put every step like half a meter.
So let's say that this is your point, right? And let's say your goal is somewhere here, right? What would happen if you picked a super large point? What would happen if you picked a super large path length, right? Let's say that this is a valid point, right? Let's say that this is a valid point, right? You would go here and you would take another point, let's say here, right? But as you can, okay, this obstacle is bad. Let's say, so you would see that it intersects, right? Which means that you have to come back all the way here to plan your next point, because this is not going to happen. This is an invalid point, which means that it does not get added to the tree. So you have to pick another point like this and then go. But if you had a smaller set of points, you would only be backtracking, let's say from here, only this much. That's one of the reasons why your path length becomes important, because it decides how much you'll be backtracking each time you don't find a valid path, right?
You could always do as far as you can go, right? Once it's
Right,
long.
right.
Yeah.
That is definitely, again, that's a heuristic. It depends on the relative sizes of your obstacles, let's say. That's an important consideration. If your obstacles are super small, then you choose your path length accordingly. If it's too big, relative to the robot, obviously, you choose your path length accordingly. So that's a heuristic. So one of the things that we can do is we can do Voronoi biasing, which is sort of explicit. We can also do something called goal biasing, right? So as you know, every time you're picking a new point, we are checking if it connects to the tree and we connect it or not connect it, right? From time to time, what we can do is we can, instead of picking a random point, we pick the goal point and see if it connects back to my tree, right? So what that allows you to do is that you reach your goal in far lesser iterations than if you were to just keep going and hope that your random point is the goal point. So that's called goal biasing and allows you to cut short the number of iterations needed to go from start to goal. Another interesting option is bidirectional RRT, right? Which is basically you have a start node, you have a goal node, you start doing RRT from both sides, right? And you hope that they meet somewhere. And obviously that's going to be much faster because you're running parallelly these two processes, and you can think of it as cutting the time in half, let's say.
How do you solve puzzles? You know, these mazes. You know mazes where you say, you know, the mouse gets here, you have to get to the cheese, and you know, how do you solve them?
Goal outwards,
Eh?
from the goal outwards.
You go backwards. Yeah. Many people go backwards, the very good ones, and forwards at the same time. So same thing here. Okay?
So one thing to remember is that bidirectional RRT is not two trees. It's one tree in the end. It should connect back to one common point. Okay. So quick summary on RRT is that basically you have one parameter essentially that controls the overall output, right? You have a good balance between greedy search, which is your random walk and you know the naive choice, and you have an exploratory component to this, which is basically a Voronoi biasing, and super simple to implement. And I urge you guys to try it once, to try and see if you can do a quick RRT. Obviously, one of the core components that is a disadvantage is that since we are using nearest neighbors, the efficiency of your nearest neighbor algorithm decides the efficiency of your tree planning, right? And because it's probabilistically complete, you have an unknown rate of convergence. You can never guarantee. So that's another thing. So probabilistic complete, the chances of convergence reaches 100% as your number of iteration reaches infinite. So that's the basic issue with RRT. A quick walkthrough. We have 15 minutes. A quick walkthrough on that was the probabilistic algorithms, the sampling based algorithms. Now we come to D Star.
In the first or second slide, there was that single tree and bidirectional tree. So that bidirectional tree was not the bidirectional RRT. Right?
It was.
That is.
Yeah. Bidirectional means it's one tree going from both sides. There are no two trees. There's one tree. You do RRT from start to goal and goal to start. So ideally what will happen is at some point you will have a common node which connects the two trees. That's bidirectional. Okay.
So for the bidirectional one, you actually wait till one specific node is common between two sets of trees, or do you wait for them to be in the same general area?
That depends, right? Because if the same general area has an obstacle,
Right.
it's basically useless, right? You need to find another common point. But again, that's a heuristic. You can keep going until the last edge node of one tree and the edge node of another tree are within a certain region, and then you can manually plug them in by some another via node. You can do that.
You know, your friend is in the big M, and you are here, and you want to meet. So you start walking towards his direction, he starts walking towards your direction. That's the bidirectional algorithm. Now, how smart you guys, you can get lost, right? I mean, because he comes from one building this way, and you go from that other way, and you don't meet. But if you are very well informed, and you know about the general path that you are taking and he is taking, then the chances of missing each other lessens, right? That's the bidirectional.
So let's say you see him there and you wave to each other, doesn't mean you have met, right? So what you do is then you go to some super simple planning, which is like a straight path, and you join them. So you don't actually have to connect them. But then again, you can do the goal biasing. In this case, this node's goal is this node and this node's goal is this node, and you can force them to meet. Yeah. Okay. D Star. Anthony Stentz. This guy is again super cool. You should read his two papers. One of them is D Star and one of them is Focus D Star. Both of them he wrote. Definitely read it. Super simple again. This is basically D Star is a focused, is an informed incremental search, right? Same as A Star, but with certain caveats, right? D Star, full form dynamic A Star, which is basically A Star, but in case of A Star, your edge weights, you assume that they are constant from start to end. You cannot have dynamic edge weights, which means that if you are going from here to, let's say, Loonies, the bridge broke, right? A star will never get you there. You have to know that the bridge broke, give that area a higher cost, and plan again. In case of D star, you reach the bridge, you see it's broken, you take the other way around as you go. That's the dynamic concept of D star. One of the things that A star does is that once you have, as you're going through, once you have the goal, basically your past information is thrown out, right? Which means that you do not keep in mind all the things that you discovered as you were planning. But D star uses that to its advantage to replan dynamically as you're proceeding through your search. As I mentioned, focus D star and D star light. Check these out. Slightly different, complicated algorithms, but no one uses D star in real world examples because D star light is currently the so-called standard for dynamic planning. So take a look. We should have a video.
D star light.
Yes, we should have a video on D star light.
So what we need now is a deep D star or a D star net. Okay?
Okay.
I'm just saying, man. I'm surprised. Can you Google deep D star or D star net? I mean, maybe they have already, somebody has written a paper on it.
Okay. As expected, YouTube doesn't open, so take a look at the link.
What are we looking at?
We are looking at a sample video of how D star works.
Where's the video?
It doesn't play because of UMD secure
Because?
of the internet.
The
It
internet?
yeah, this is on YouTube, right? So it's not playing. Okay.
Oh, you don't have a connection? Maybe you
I-
can go hardwired or something
Yes. Oh well.
from the monitor.
Yeah. But definitely the link is there. Take a look. Okay. So coming to the details of D star. As we mentioned during A star, we have very similar data structures, lists that we maintain, but there are some new ones, right? You have a new list in this case, which is those nodes that have never been looked at, which have never been in the open list. The open list is basically a list of nodes that are currently open. You have a closed list, which is that when the node is no longer open. You can consider new, open, and closed. I mean, all of these are not exactly lists, but you can treat them as flags, right? Flags which are assigned to each node instead of considering them as lists. You have a raise list, which is that if a node currently has a higher cost, which means that if the edge cost for that node is higher than previously, then you put it with a raise flag, which means that the cost has gone up, and the opposite with lower, which means that the cost has gone down, right? These are the basic data structures. The algorithm consists of two parts. One of them is expansion and one of them is obstacle avoiding, right? So you first pick a node from the open and you check out its values, right? The costs. Previously, you remember for A star, we had the heuristic cost plus the cost to go. So similarly, you evaluate the values, right? And based on these values, you have the 8 connected neighbors, right? You propagate these values to all of your 8 connected neighbors, and you put all of them into your open list, which means that they are now under consideration. One of the things about D star is that the algorithm goes backwards from goal to start. And as you open or evaluate each node, you have a back pointer. Why is this a back pointer? Because you're going from goal to start, which means that when you go after you have planned from start to node, they are just straight pointers. So that's every node has its back pointer, which is the next node to go to. And we know the cost to go from one of these nodes to the other node, which is, if you remember, 1.4 and 1, or 14 and 10, or whatever, based on our Pythagoras. When the start node is encountered, as in when it is in the open list, that's when your algorithm ends, and from start we follow the back pointers to our goal. And that's the basis of how we iteratively expand each node. Now, the idea is that when an obstacle is detected, right? Okay, so you plot a path, right? You proceed down that path, you hit an obstacle. At that time, you have to do the replanning, right? So which means that given the point that you're on, all of its neighbors are put back to the open list. And their costs are raised, which means that you put them with a raise flag and their costs are raised. But before you physically raise the cost of all these nodes, you try and see, is there a way I can avoid this? If it is, then you try that. Otherwise, what you do is you put the raise flag and then there is a wave of back propagation. So every node that had a back pointer, you raise their cost, their cost, their cost, which means that till now, from here to here with this as an obstacle, this is a bad path, right? Which means that all of the points that led you here also have a higher cost, which means that you try and avoid that. So that's what it means by propagate all of the back pointed nodes with the raise flag. If let's say that after you come here, you can change the cost, only till here do you have a higher cost. After that, this one is lowered down so that now you know that this is a good path. Wherever you can lower, you lower. And again, given that this has been lowered, all of these points have also been lowered, right? So this remains with a bad cost, high cost, and this lowers everything. So now you know that you can avoid and go. So as I had done for A star, this is what the cell looks like, right? This is, let's say that you are at x1. These are your 8 connected neighbors. Your x9 and x8 are your obstacles, and the others are available to you. So x, y, whatever, these are the states of the robot. Like you are at x, you want to go to y. So these are states of the robot. B of x equal to y, which means that it's a back pointer from x to y, which means that you have come to x via y. You have another value called C of x, right, which is the arc cost from x to y. This arc cost is this 1.41 value, right? That's the amount of cost it takes to go from x1 to x3, let's say, or x1 to x2. You also have the current measurement. Now, as you remember, because this is dynamic, you need to keep yourself updated about the cost. You can't just stick to a fixed cost, which means that as and when you get a sensor reading from your robot, let's say, that is your R of x comma y. That can be lower or higher than the estimated cost. Because let's say that initially you were under the assumption that x1 to x9 was 1.4, right? But once you reach x1, you find that it's a obstacle from your sensor reading. You take that into account, which is R of x comma y. You have the T of x flag per node, which is the raise, open, new, close, whatever. And H of x is your actual path cost, which is the complete path so far. And you have K of x, which means since this node, some node was in the open list, what is the smallest H of x? Because we obviously want the least path cost, right? I will try and explain D star in some more detail in the next class, but till then it would be nice if you go through this link 38 to 59, which is basically a solved example for D star. You are not going to be using D star in any of your projects, but if you want to do some real world robotics applications in path planning, you definitely need to know this. So take a look at slides 38 to 59 of this How We Chose It slides, and if you have any doubts, we can either solve them next class or probably spend some time in office hours with this. So that ends D star. We have around 5 minutes for any queries. All good? Okay. Yeah. Sorry. Yeah. Deadline?
Thursday? Or
21st. Yes. Project 1 phase 2.
It says differently on Elms, but I guess we're not using Elms.
We are not using Helm. Sorry. I mean, it should be available to you on your PDF.
Yeah.
Stick to the PDF.
So then, I just to tell you, like someone changed it in Canvas, it says 29. So,
29th. Okay.
For you to know.
Okay. My bad. Whoever, I'll deal with it. But stick to your PDF. And please, I think from now on, you will not find any submission link in Canvas. So stick to the website. the submission portal for that website. And I am repeating myself again. Please follow the submission guidelines.
It's good to repeat.
Yes. Please follow the submission guidelines. We have had issues with Project 1 Phase 1. People haven't submitted correctly, and that means that the autograder fails, which means that you will get a 0 for the moment until I can go back and manually fix all your submissions. The idea is you have a folder that you will submit called code.zip, right? When I unzip this, there should be a folder called code. Inside that, you will have all your files, right? That's how it should be. What people have submitted, and the reason why it's failing, is that your code.zip, when I unzip, directly gives me all the files. That's not supposed to happen. So please ensure that this mistake does not happen when you are submitting the second assignment, Project 1 Phase 2. Okay?
Are we